Hello, so this is section 5.5 video 2. I hope everyone's week is going well. Like I've said, I think chapter 5 is my favorite chapter in all of linear algebra. Just looking at eigenvalues is so fun. And we're just going to keep doing that. So last section, or video, we sort of looked at this matrix, decided that it has complex eigenvalues, and then stopped there with this example, right? So after that, I wanted to quickly review some complex number knowledge that we would need moving forward. And so now that we have that, I want to actually find the eigenvectors of this matrix. And so it turns out we're going to do this in the, I guess you could say, traditional way of finding eigenvectors. That is that we're going to subtract an eigenvalue from the diagonal, row reduce, and look at the parametric vector form solution and find an eigenvector. Except, notice that this matrix is going to have the unique property that, when we subtract lambda 1 from our diagonal entries, we get complex numbers in our matrix. So we get a complex matrix, right? So this would be 1 minus 2 plus I, and 3 minus 2 plus I. So here we get negative 1 minus I, 1 minus I. And now we have to row reduce this matrix. So I don't know how to divide complex numbers well enough to be able to make a ton of sense out of these two sort of relationships. Thankfully, we don't have to know that much, right? So remember, what we want to use is row 1 to get rid of this entry, right? And then, if any luck, if lambda 1 is actually an eigenvalue, we will also get rid of this entry in row 2. So we could do that in a couple of ways. What I'm going to do is use the correct division to get rid of this entry. Right, so what we want is we want to multiply this by something to get 1, and add it to, multiply this by something to get negative 1, and add it to this row. So what I'm going to do is do negative 1 over negative I minus 1, row 1 plus row 2. So notice that this times this gives me negative 1, which will make that 0. So I don't have to worry too much about that entry. What I do need to check is that this entry, when I multiply 2 by this number, gets me 1 minus I. So to do that, I need to calculate what is 2, or gets me negative 1 times this, right? So this should eventually turn into 0. So I want to multiply 2 by negative 1 over negative I minus 1. So this would be 2 divided by negative I minus 1. And so remember, we do complex number division by multiplying the top and the bottom by the conjugate of the denominator. And so here, notice this is the conjugate. So at the top, I get negative 2 plus 2i. Here I get, the entry attached to I is equal to 1 or negative 1. It doesn't really matter. Negative 1, so I get negative 1 squared plus negative 1 squared. This is equal to negative 2 plus 2i over 2, which is equal to negative 1 plus I. And so notice, this is what I'm adding to this, which gets me 0. And so in fact, I do get a row of all zeros, and it turns out that even though I would have never been able to guess from looking at it, these two rows are linearly dependent. So when doing this row reduction, like I said, kind of let the matrix decide for you what row reduction steps you're going to take, right? I let the matrix decide for me here by just saying, okay, this one had to be this way to make this 0, and then if this is an eigenvalue, the other entry should follow. So now we need to do one more step, right? So we'll kind of separate this off a little bit. So this is sort of an interlude, so to speak, of the row reduction process. And so now we're continuing the row reduction of this matrix down here. And I want to turn that first entry into a 1. So I'm going to multiply 1 over negative I minus 1 row 1. And so notice again, that just immediately turns this entry into a 1. And then I'm basically going to do something kind of similar. I'm going to, well, just do negative 2 divided by negative I minus 1. And so this is equal to negative 2 times negative 1 plus I over the conjugate, which we've already actually calculated the conjugate of this, right, to be 2. And so you could actually calculate that this is just equal to 1 minus I. Because we've kind of already done the calculation here, where notice here we calculated 2 over negative I minus 1. Here we're doing negative 2 over negative I minus 1. So it should just flip the signs of the eventual answers. And so we've now got this complex matrix in row-reduced echelon form. And so if you'll remember, this corresponds to a homogeneous system of equations, where again, I've just got this complex number here, but that's okay. And I'll just do the same subtraction. And so this corresponds to an eigenvector. Well, if I let x2 be equal to 1, 1 minus I, 1. And this is an eigenvector for lambda 1 equals 2 minus I, plus I, excuse me. So, besides having to do the complex number division, this sort of a process isn't that much different for complex numbers, right? Once we got to the row-reduced echelon form matrix, I got to my eigenvector in the exact same way, right? I put this in parametric vector form. This is the vector that corresponded to that parametric vector form solution, and so I can just call this an eigenvector. So now you might think we want to do the same thing to find the eigenvector for v2, but I want to spend most of the rest of this video convincing you that there's actually an easier way to find v2. And so the time I spend convincing you will probably be longer than you spend the entire rest of this course finding the second eigenvector for any complex eigenvalued matrix. So let's see. Yeah, I'll erase this and I'll save the eigenvector because we will need that later on. Save that. Save that. All right. So, why is finding the next eigenvector easy? So to do that, I want to introduce a couple more definitions. So for any complex vector, v, we can split into its real part which will denote Re of v, and imaginary part which will denote Im of v. And so, again, the real part is just all of the coefficients corresponding to, so if we're looking at this vector v1, the real part of this vector is just the coefficients attached to the real entries of both of these vector entries. And the imaginary part of this vector is the vector containing the coefficients attached to the imaginary parts of these entries. Right, so in general, we'll say if v is equal to a1 plus b1i and a2 plus b2i, then the real part of v is the vector a1, a2, and the imaginary part of v is the vector b1, b2. So basically, it's just two separate vectors, each of which encode the real parts of each number and the imaginary parts of each number. And so then notice for every vector v, v is equal to its real vector plus I times its imaginary vector. All right. So given this, we can actually now also define the conjugate of a vector. So here we've got this definition. And so the conjugate of a vector is just exactly basically how we define the conjugate of a number. It's just the vector bar v, so it's kind of confusing because it's a bar over the vector notation. But this is just the real part of v minus the imaginary part of v. And so notice here in this example, the conjugate of v1 would be equal to -1, 1, minus 1, 0 times I. And so this would be equal to -1 minus I, 1. And so I want to save this and come back to this and then define and point out one more thing. So we've now got, we can split a vector up into its real and imaginary parts. The conjugate of a vector is defined much in the same way that a conjugate of a number is defined, right, where you just swap the signs of the imaginary parts. And so we've got that the conjugate of v1 is just -1 minus I, 1. So notice the real parts of the vectors did not change, but the imaginary parts signs flipped. So it turns out we can define the conjugate of a matrix much in the same way as well. So the conjugate of a matrix of a, we'll say of a complex valued matrix, although this could be defined for any matrix. It just doesn't make a whole lot of sense if A doesn't have at least one complex number, is the matrix a bar whose entries are the conjugates of the entries of A. So what this means, just take your complex matrix A, take all the conjugates, right? And so notice for this matrix, for example, the conjugate would just equal the original matrix because there are no complex parts. But all you're doing to find the conjugate of a matrix is just taking the conjugate of each individual entry. And so the last thing, before we move on, the conjugate as an operation is multiplicative. So that is, if I've got two complex numbers z1 and z2 and I take their product and then take the conjugate, this is equivalent to taking their individual conjugates and then taking the product. So what this means, and I won't do too much detail to work this out, but I'll leave this as an exercise. If you were to take a matrix vector product and take its conjugate, it would be equal to the conjugate of A times the conjugate of X. So you can split conjugates up across individual products, and you can split conjugates up across matrix vector products. And this fact actually just follows from this fact. So this fact is what we're going to use to calculate our second eigenvector for this example. So next up, I want you to notice that lambda 2 in this example now, so we're going back to the example, is equal to the conjugate of lambda 1. Right? So notice that 2 minus I is equal to the conjugate of 2 plus I. All right. So we also know from the work we've done before that A times V1, this vector, is equal to lambda 1 times V1. And you might see where I'm going with this, given what I've got on the board. Like I said, just cool math. So you could actually probably now calculate an eigenvector for lambda 2, given all of this information. So we've done a lot of problems like this, where we kind of start with what we want. We know we eventually want an eigenvector for this value. So actually pause here and try and work out the rest and find an eigenvector for this, given what I have on the board. Because it's only a couple more steps, really. So anyhow, pause here, try and work out the rest. All right. So what we're going to do is we're going to take the conjugate of both sides. And remember now, the conjugate is multiplicative, right? So this is equal to conjugate A times conjugate V1, which we have here, is equal to conjugate lambda 1 times conjugate V1. Well, and now we're pretty much done, because notice this implies, well, I've already said the conjugate of A is just A itself, because A itself doesn't contain any complex numbers. We know the conjugate of V1. We're not worried about that. Oops, and I forgot to put a conjugate sign there. We know that the conjugate of lambda 1 is equal to lambda 2. And so this is equal to lambda 2 times V1. And what did we just show? That it turns out that the eigenvector for lambda 2 is just the conjugate of the eigenvector for lambda 1. So cool. And so notice now that this shows a few things, and we'll end on this. That first off, we can always do this, right? That all of the work I just did and erased shows that, if we have two eigenvalues which are conjugates of each other, then we can always find their eigenvectors by just taking the conjugates of the eigenvectors. But this also shows that if lambda is an eigenvalue, or we'll say a complex eigenvalue, for matrix A, and we'll say with corresponding eigenvector v, then lambda bar, the conjugate of lambda, is an eigenvalue for A with eigenvector v bar. So what this shows, two things. Well, one big thing, that if I've got a complex eigenvalue, its conjugate is always an eigenvalue as well. So complex eigenvalues always come in conjugate pairs, which means that for these 2x2 matrices, we're never going to have a matrix with one complex eigenvalue and one non-complex eigenvalue because of this fact. On top of that, if I've got my complex eigenvalue and an eigenvector, I immediately know how to not only find the other eigenvector, but also the eigenvalue. They're just always conjugates of each other, which is just so crazy. You know, it's like one of those things that just like seems like this crazy coincidence. But yeah, no, so that's the case. So eigenvalues and eigenvectors, when they're complex, actually turn out to be pretty straightforward. And again, you know, I spent 10 minutes sort of proving this fact for this matrix, but you know, now moving forward, once we've done the work for one, it's just an extra line for the other. So next video, we're going to finish up this section by going over some applications of these matrices to linear transformations in R2 and sort of looking more at the geometry of what's going on. And that's also just awesome.